Hi, science friends. We have 2 more lessons left until Christmas break, so I'm really excited for that, and I know you all are too. Well, 2 lessons and then a study guide and a test, but two video lessons, and so I'm excited about that for you and for me as well. So I'm throwing this bell ringer up today. If you are looking for a few extra credit points and feel like you need to practice phase diagrams a little bit more, go ahead and try this bell ringer if you'd like. Just send me an email with the answers for those 4 questions, and I'll give you a few extra credit points if you do that today. So this is a valid today only thing. Today is Tuesday, or when you're watching it, it's today Monday, but when you're watching it, it's Tuesday. So send that to me sometime today, and I'll give you a few extra credit points there for attempting that. But what we're really going to talk about today is the ideal gas law, which can be a little tricky, and then Avogadro's law, which should be really honestly just review for you. So let's look at the ideal gas law. So the ideal gas law says that the number of moles of gas is directly proportional to the number of particles, okay? And we're going to see that demonstrated more through Avogadro's law. So when we look at the ideal gas law, I typically look at it in the formula PV equals nRT. That is the formula for the ideal gas law. Now, you can rearrange it to solve for any different variable. So you could rearrange it and solve for P or V or T or whatever. But I typically like to do it as PV equals nRT, okay? And this is on your formula sheet. You'll see it on your formula sheet up here at the top. I can't write on this, but I can kind of square it. So you'll see it up there at the top. Yours has an equal sign in it. Mine is not showing up for whatever reason, but it's on your formula sheet. So you should recognize most of these variables because we've talked about them. So P, that stands for pressure. V, that stands for volume, okay? Now we haven't talked about N or R. We'll come back to those in a moment. But T stands for temperature, and that has to be in Kelvin, okay? I'm going to write a little K up here because that has to be in Kelvin. And I'm also going to write an L up here because that has to be in liters. Sometimes in the past, with some of our other calculations, we were able to use the volume in milliliters so long as both volumes were in milliliters. But that's not true for this. We have to make sure we are in liters for these ideal gas law calculations, okay? So when we, let's talk about these other 2 variables. So N is equal to the number of moles, okay? And R, as it shows down here, is equal to the ideal gas constant. Now, I've labeled the ideal gas constant here below, and I forgot to put the units on it. Honestly, I could probably just take this off of here because I'm going to explain it in a different way in just a minute. But this is one of the ideal gas constants, 8.31 liters kPa per mole Kelvin. Now, you look at that and you're like, man, that's a lot of units, Miss Brown. And you're right, it is. But if we solve for R, like is done in this equation right here, our units would be, the pressure would be kPa if we did it in kPa, okay? So we've got our kPa here. The volume would be liters, so we've got our liters there. So we see liters kPa, that dot means they're multiplying by each other. The N we said is moles, and so that's what we have here. And the T is the temperature in Kelvin. And so the ideal gas constant incorporates the units of all of those parts. And you can't simplify it. You have to write it out that way. That is the correct units for the R value, okay? So on your formula sheet, you see the ideal gas constants right here, maybe, if you can see where I'm touching. But beneath that, you'll see that you have 3 boxes of ideal gas constants. And so take just a second to look at those. So the first one, it says RATM equals 0.0821. The next one says RMMHG is 62.4. And then the last one says RKPA equals 8.314, okay? And then notice the units at the end of them I don't think I can highlight it. But up here at the top right corner, these units in the top right corner are kPAs, versus here they're mmHgs, versus here they're ATMs, okay? So the ideal gas constant that you use depends on the pressure that you've been given in the problem, okay? So if your problem is asking you to find the temperature if the pressure is at, 100 ATMs, then you have to use this value because it is the gas constant in the unit ATM. If your pressure is given in mmHg, or torr for that matter, since those two are like the same, then you'll use the gas constant of 62.4, okay? If your pressure is given in kPAs, then you'll use the gas constant of 8.314. So that's the kind of tricky part. You have to make sure that your pressure matches your gas constant, okay? So just be advised of that, all right? Now, there's one tricky thing. If you're doing a PV-nRT problem and it asks you to solve for P, and so it doesn't give you a pressure because you are trying to find the pressure, then you can use any of the R values you want. You can use 0.0821, you could use 62.4, or you could use 8.31. The catch is that you have to make sure you put those correct units on. So if you use the 62.4, your units on the pressure would be mmHg. If you use the 0.0821, your units on the answer that you would find would be 0.082, would be ATMs, sorry. And if you use the 8.31 as your R value, then your units on your answer would be kPAs, okay? So that's how that works, all right? So let's take a look at a practice problem. And so I always like to first identify what all my variables are. So it says you fill a rigid steel container that has a volume of 20 liters, so that's going to be our volume, with nitrogen gas to a final pressure, so this is our pressure, of 2 times 10 to the 4th kPa at 28 Celsius. So that's going to be our temperature, but we're going to have to convert it to Kelvin. So 28 plus 273 is 301 Kelvin, okay? And the question asks us how many moles of N2 does the cylinder contain? So moles is N, so that's what I'm trying to find. So we'll write our equation, PV equals nRT. And I'm going to plug in all the numbers that I have. Okay, the first number that I have, the P, is 2 times 10 to the 4th. So I'm going to write that out as 2 times 10 to the 4th kPa. Okay, the V is 20 liters. The N is what I'm trying to find, so I'm going to leave that as N. Now, the R, okay? Here I'm in kPa, so I have to use this R value, 8.314, okay? 8.314 liters kPa per mole Kelvin. And then my temperature is the last thing, and that's 301 Kelvin, okay? I want to go ahead and cross out my units, and so I'm going to cross out K because there's 2 of those. I'm going to cross out kPa because there's 2 of those. Liters because there's 2 of those. And so all I'm left with is moles, okay? Now if you remember, we are solving for N, and N stands for moles, so it makes perfect sense that our answer would be given in moles, okay? And so now all we have to do is, just like you would in math, isolate the variable and solve for N, okay? So essentially what we're going to do is we're going to take these 2 values and divide them by those 2 values to get N by itself, okay? So in my calculator, I'm going to type 2 times 20, and that gives me 40, over 8.314 times, and I forgot my 10 to the fourth. I need to keep my 10 to the fourth there, okay? 8.314 times 301, and that's 2,502.5, okay? So now when I divide that, I personally am just going to divide 40 by 2,502.5. And I got 0.01598, okay, times 10 to the 4. So now I have to move this decimal 1, 2, 3, 4. And so my answer should be 159.8 moles. Okay? And that's how we would solve that problem. That's how many moles of nitrogen the container will hold. Okay? So you have 2 problems to try on your own. I'm going to give you a little bit of guidance for them though, because they are slightly tricky. Okay? So let's look at the first one. It says what pressure, so that's what I'm trying to find. I'm going to solve for P, will be exerted by 0.45 moles, so moles is going to be our N, of gas at 25 Celsius, so that's going to be our temperature in Kelvin, and 25 plus 273 is equal to 298. Okay. If it's contained in a 0.65 liter, so that's going to be our volume, vessel. So when we set up PV equals nRT, we're going to solve for our pressure, so we'll leave that as P. We've got our volume of 0.650, our N of 0.450 moles. We don't have our R, and then we have our T of 298 Kelvin. So what R value do we put in here? Well, usually we look at the pressure and see what the pressure is. But here we're not given a pressure. So as I mentioned earlier, because we're not given a pressure, we can choose any R value we want. You could put in 62.4. That doesn't get a decimal. 62.4 mmHgs. You could put in 8.314 kPAs, the whole unit, not just the short unit like I'm writing. Or you could put in 0.0821 ATMs, okay? And remember, the units are liters times that pressure unit over mole Kelvin, okay? It doesn't matter which one you use, but whatever one you use, your pressure is going to have that same unit. So if you use 62.4, your pressure will be in mmHgs. If you use 8.314, your pressure will be in kPAs. And if you use 0.0821, your pressure will be in ATMs. Okay? So choose one and solve it. When I give you the answers here in a little bit, I'll give you the answers for all of those. Okay? So that's the first one. Now let's look down here at the second one. What volume will 12 grams of oxygen gas occupy at 25 degrees Celsius and a pressure of 52.7 kPa? Okay, so I see this Celsius and I know that's going to be my temperature. But again, we're going to have to convert it. So I'm going to convert it and it'll be 298 K. Okay, this kPa is going to be my pressure. So I'm going to label that as P. Because this is in kPa, for our R value, we're going to want to use the R value for kPa, which is 8.314 liters kPa per mole Kelvin. So make sure to use the right R value because we're in kPas. Can't use any of the other ones on this one. Okay? So I've got my T, I've got my P, I've got my R. But what I don't have is my N and my V. Well, my V is what I'm solving for, okay? But what about my N? How am I going to figure my N? Well, this problem actually occurs in 2 steps. You know how to figure your N. We've done this for a long time, since like Unit 2. If you're given 12 grams of oxygen gas, how many moles is that? So we know 12.0 grams of oxygen times in 1 mole of oxygen, what is the molar mass? Well, oxygen is 16 and it's O2 because it's a Hofbrinkel. So it's 32 grams per 1 mole, okay? So you can solve this, 12 divided by 32. And so 12 grams of oxygen is ignore that point, 0.0375, okay? 0.375 moles of oxygen, okay? So while that's not the answer to the problem, we need that to be our N, okay? So this problem was actually kind of had an extra step. We had to find N before we can solve it. So now we have PV equals nRT. We're solving for V. We've got our P, we've got our T, we've got our N, and we've got our R. So we have all 4 things that we need except for the V, and that's what we're going to find, okay? So I'm going to let you finish this and pause for right now, and then I'll come back in just a moment and work it with you. All right, let's take a look at these together. So on the first one, I have all of the answers here in the box, depending on which way that you worked it. So 12,873.6 mmHgs, or 1,715.2 kPas, or 16.94 ATMs, okay? And then on the second one, you should have gotten 17.63 liters, assuming I've done all of my math correctly here. Okay, so hopefully you got those. Now I did guide those, you through them a little bit, but if you have any questions about them, please reach out and I'm happy to help a little bit more with them. Okay, so that's all we're going to do for the practice problems for the ideal gas law. But let's talk just about a minute about what is an ideal gas. So an ideal gas is a gas that follows all the gas laws at the conditions of standard temperature and pressure. Ideally, these gases don't really exist, but some gases have ideal gas law behaviors. And so an ideal gas law would actually show a flat line if it was graphed, meaning the pressure plotted against one another, okay? And so while we don't see perfectly flat lines here, there are some gases that do come a little bit closer, okay? I'm not going to quiz you a lot on what an ideal gas is, so don't sweat that. So let's jump in next to Avogadro's law. So like I mentioned, we have talked about this before, we just didn't give it a name. So Avogadro's law tells us that equal volumes of gases at the same temperature and pressure contain an equal number of particles. So at STP, 1 mole of any gas equals 22.4 liters. You should know that number. We've done that conversion before, right? So basically it's telling us if we were to fill up a balloon of any gas, be it oxygen, be it nitrogen, be it chlorine, whatever gas, the balloon is going to be the same size, okay? If it has the same number, 1 mole of the same, 1 mole of oxygen or nitrogen or chlorine, they all take up 22.4 liters of space. And so all of those balloons are the same size, okay? Now, that's not necessarily true for all things, but gases are that way. So, for example, if I gave you, remember 1 mole is 6.022 times 10 to the 23rd particles. So if I gave you 1 mole, that many particles of marbles, it would take up, well, actually a lot of space, right? Because that's a lot of particles. But if I gave you 1 mole of bouncy balls, big bouncy balls, you know, like the let's say basketballs, it's going to take up even more space, okay? Because it's a much bigger because the bouncy ball is or a basketball is so much bigger than a marble. But gases are not that way because they don't pack in space. Remember, they don't condense in the way. They fill the volume of their container. And so that's what Avogadro's law says. And so basically what we're going to do is do some conversions. And you've honestly done conversions just like this in stoichiometry. We just didn't call it Avogadro's law. So these should be super easy. So let's look at them together. Determine the volume. So we're trying to find the volume in liters occupied by 0.202 moles of a gas. So we're going to start with what they give us, 0.202 moles, okay? And so we know that 1 mole is 22.4 liters. And so literally, that's all we do. It seems so simple, right, after you've done it for a while. And so you get 4.52 liters of that gas. The next one, how many oxygen molecules are in 3.36 liters? So we have to get to molecules of oxygen gas, but it doesn't matter what gas it is because all gases are the same. So we know there's 22.4 liters in 1 mole. And then in 1 mole, we have 6.022 times 10 to the 23rd molecules. Okay, so if we do that, 3.36 times 6.022 divided by 22.4, then I get 0.903 times 10 to the 23rd. Or you might say 9.03 times 10 to the 22nd. Either would be fine. Okay. Both of those would be correct. Okay. And then the last one, I'm running through these really fast because I feel confident in your ability to do them. So determine the volume in liters occupied by 14.0 grams of nitrogen. So this is nitrogen 2 because it's a Hofbrinkel N2. Okay. So we're going to have to do a gram to mole conversion here. So again, we're just doing a little bit of stoichiometry. So nitrogen, 1 nitrogen is 14. So N2 would be 28 grams per 1 mole. And we know 1 mole would be 22.4 liters. Okay? So 14 times 22.4 and then divided by 28 gives me 11.2 liters. And always make sure that your units cross out. Okay? You all know that's how I feel about that. And that's, whoops. Good practice, okay? And so there's your answer there, okay? So you'll have 3 of these to practice below on the next slide for me, but below for you. So pause right here, practice those 3, and then come back and check with me. So here's the answers for these practice problems. You all should have gotten those pretty easily, 16.62. 690.7 times 10 to the 23rd, and 4.48 liters, okay? So those are pretty easy and straightforward. So you have an assignment today on the ideal gas laws, and then I think the rest of what you have is mixed practice. I don't actually think you have any Avogadros to do today. I think your Avogadros practice is going to be tomorrow. So the mixed practice is going to encompass ideal gas law, combined gas law, Boyle's law, Gay-Lussac's law, and Charles's law. And so it's up to you to determine which variables you have. As you read through those questions, make sure to identify, write the variables, just like I do. When we go through these, I underline them. Not right here. Yes. When we go through these, I underline them and I label that, okay? Do that when you go through those and you'll see what you have, and that will help you determine which equation to use, okay? If you have any questions, reach out, and if not, then you'll have a great day.